So now we have question C, and we've got a ball being released at a height greater than r but less than 2r, and it will lose contact with the track at an angle theta as shown on the diagram below. So we covered all bases so far. The first one we were considering where the ball stays in contact with the track and comes up below r height. Then we've considered the case where the ball can continue around and do the loop, and now we're considering the case in between that, somewhere in here where the ball ends up in a place where it will fall off the loop and lose contact. We have to derive, moving on down here now, derive an expression in terms of theta for the velocity of the ball at the time it loses contact with the track, and explain your reasoning. Okay, well, if I'm going to reason this out, I think it's pretty important to draw or to consider the forces involved. I don't know if the energy considerations will help in this because we're not given a specific height, and I guess it's going to be, the height of release will be between r and 2.7 r, but not equal to those, and but somewhere in between. So we would write it like this for h. Okay, I haven't drawn that very well, but I think that might be irrelevant. So considering the forces, there has to be a centripetal force towards the centre, which is causing the rotation, and that centripetal force is going to be greater than the velocity required to keep it on the track. Did I say that right? In any case, that's going to be there, and that centripetal force in this case, because it's above the vertical, above the horizontal, that centripetal force has to come from a component of gravity, which is, so gravitational force Fg is down here, and there's a component in this direction here, yeah. So, and that will make up a right-angled triangle to add the two components of the force due to gravity. And we'll find that, excuse me, because we're interested in that component of gravity, it's going to be Fg, force due to gravity, sine theta equals mg. And you can mess around with the geometry to try and work that one out, because the triangle is not this, let's see if I can draw it here. You've got this triangle here, which you've created. Oh, hang on, where are we? And that's not the same triangle. So it's a triangle that's dealing with the radius and the distances and all that kind of stuff. What we're considering is, I'll draw it over the top in orange. We've got a centripetal force here, and we've got a force due to gravity here, and this is our angle here. Okay, so and sorry, that's not our angle. That's our remaining component of the force. Let me blow that diagram up just a little bit over here, so we can see and identify just what's going on. Okay, I haven't drawn it perfectly, but you should be able to get the idea. So this is Fg. That's our resultant force. We've got Fc here, which is going to be equal to mg sine theta, because the theta from this diagram here is going to be equal to this angle here. Okay, so the opposite angle to that side, Fc. Anyway, you can mess around with the geometry to try and work out and see how that works, but it works very nicely. And what we can do with that is mv squared over r, because we're centripetal force equation, so we use the big R, equals mg sine theta. So we're again just going back to what we're trying to do, trying to get an expression for the velocity of the ball in terms of theta. So our masses will cancel out, and velocity squared then will be equal to g r sine theta, and you could take the square root of both sides of that. So that's the expression we're after, and your explaining your reasoning is getting into the forces and saying that it's the Fc equals that component of gravity. So it goes sine theta there. So that's your explanation to link those two things. Okay, that was a little bit of a roundabout way of getting there. No pun intended for the roundabout. So D, for a release height where the height is less than r, so this is going back to the same as the first question. In fact, it says that later. The solid ball is replaced by a frictionless sliding block. Okay, that's eliminating the rotational kinetic energy aspect. Same mass, similar size. Explain any similarities or differences from the motion for the rolling ball in part A for this question. So, what's the same and what's different? Okay, things are the same. They're both going to go up to the same height and just kind of shuttle back and forth. So for the ball and for the sliding block. So that's the same. It's the same path. What's different? I've just explained why they're the same is because the gravitational potential energy is conserved on both sides. That same height for the same mass and same gravitational field. What's different though is because it doesn't have to rotate, the sliding block should have more kinetic energy linear at this point, which means its velocity will be higher compared to the ball, which will have a lower velocity. So that means if it's continuing to oscillate back and forth, then the period, or t is a better symbol, the period will be lower for the sliding block, but the period will be higher. It'll take longer for the ball. Okay, and so just trying to be consistent with my notation there, and that's it.